major health problem. It's one that we all want to run away from. But people will say, okay, so what's the big deal about that? People have been dealing with strokes for a long time. So what they have brought here is they have brought innovation into the mix, unusual levels of innovation. As Professor Ultra mentioned, Professor Bradley is heavily cited even in the Guinness Book of Records for leading edge work in microrobotics in this area. And now they are even going into the nano realm. This is really distinguished work. But that's not just the issue. The issue is they are making healthcare available to a larger set of people around the world, because this is now something that can be done remotely. So that's groundbreaking. So they are now making things more affordable and people can access this. So it is groundbreaking in the sense that these two gentlemen are now doing work that will make the world a better place. They are now doing work that will close the gap between the North and the South. Because once you get to that point where you can do things remotely and safely, you can reach so many more people. And that is what science should be about. That is really the purpose of science. I know the idealist philosophers will say, no, you should have knowledge for knowledge's sake. But I think it's Dewey in America, the philosopher of education, who has been emphasizing that we must have a mix, we must have a broader mix, and we must go towards more pragmatic education, solving real life problems. And that is the purpose. That is the reason why BUST itself was set up, because we have the University of Botswana, which is the traditional university and very distinguished in what they do, the medical fields, the legal fields. But the government also said, we need to do something more pragmatic, and then we have to have BUST. BUST is the ETH of Botswana. And so that is why we are very proud to have this privilege and this opportunity to have a partnership with ETH. And this partnership involves both academic staff and research students. And that is where the world is going to. We are all becoming a global village where knowledge flows around, and then we can share solutions, because ETH, what do they do and what are they good at in ETH? They are very good in science and technology, leading edge. So they use this to solve a lot of the problems. And, they're a major player with industries and places. We in BUST, what do we offer? We offer the hardest problems. We offer the hardest problems. So you in ETH, you have the best solutions. We have the hardest problems. Why can't we mix the best solutions with the hardest problems and make the world a better place? That is what this meeting is about today. Good morning, and you are most welcome to this session. Thank you.
Thank you, Professor Augur, for that very enticing remarks. For this juncture, we would like to request Professor Rodrigo Jamesola to introduce our speaker.
Good morning, everyone. Again, this is very protocols observed. I don't want to forget that. I always get in trouble because of that. Sorry. Now is a very momentous event, and I wore again my Filipino national costume to commemorate that this is a multicultural event. There's Representative Professor Nelson. He's an American professor in Switzerland, but he stayed in Switzerland now, and many other guests here that are multicultural and multinational. So that is the essence of BUST, that all of us come together from different cultures, different countries, and build solutions, not just for the country, but also internationally. We are very fortunate for Botswana government to have this platform where everyone can come together and build, create solutions for everyone locally and around the world. So Professor Bradley J. Nelson, I met him in South Korea more than 15 years ago, where Professor Nelson was invited as a distinguished professor in Daegu Gingbok Institute of Science and Technology, and I was just a mere postdoc. When Brad knew that I transferred in DUST, he immediately proposed to collaborate because of Brad's very long roots in Botswana. For everyone's knowledge, Brad met his wife Dana. Now you see the connection there. He met his wife Dana in Botswana when both of them were Peace Corps volunteers in Tutume. Tutume is 100 kilometers north of Francistown, for those who doesn't know. And now that's the major reason for his interest and support in Botswana's technological efforts up until now. Basically, he considers Botswana as family, and I was that vehicle to make it happen. Brad and I collaborated in both teaching and research. In 2022, Brad and his team from ETH Zurich spent 1 week to do collaboration in teaching entitled Introduction to Robotics and Mechatronics to BU's students taught by me during that semester. His multi-scale robotics laboratory in ETH Zurich came to be used and used a ball balancing robot platform that combines robot control with vision as hands-on laboratory teaching platform for undergraduate students. When his team left BUs after teaching, he donated one of the ball balancing robots to BUs. Let's give him a round of applause for that. And at the same time, Brad let my lab borrow the mini Navion. This mini Navion is the smaller version of the same Navion that we will be showing today for robotics telesurgery. I also want to highlight that Brad generously paid for the everything else or expenses for this mini Navion to be used by our students. Now there are 2 Master of Engineering students under my supervision that are now working their research on the mini Navion. Please give him a round of applause again for that. In support to BU's postgraduate students, Brad was instrumental in getting one of my Master of Engineering students who finished under my supervision to be admitted to the PhD program in ETH Zurich. His name is Lucky Mutsiwa, and he's here to do the telesurgery demonstration. Please, Lucky, can you stand to be recognized? Are you here? Yeah, Lucky is there. He is now studying in ETH Zurich. He came here because he's a grad student. I came here to do the demonstration. Another student is also our BU's PhD student, Lenny Sefatle, under Professor Ultra, who through also Brad's support was able to get a 1-year research fellowship in Zurich. Please stand up, Lenny. Lenny is now back in BUs as he's now writing research publications together with ETH Zurich researchers. And you can see how this upgrades our efforts a lot and bring Botswana, is like guided by ETH and introduced by ETH Zurich to the world. Brad has so many accolades, and we need a whole day to enumerate all of them. I selected only a few and highlight them the best way I can. Professor Nelson, or Brad, he wants to be fondly called that, rather than Professor Nelson. He wants to be more personal in dealings with everyone, has over 40 years of experience in the field of robotics, and has received a number of awards for his work in robotics, nanotechnology, and medicine. He received the Grand Hamdan International Award for AI in Healthcare and was named the Scientific American 50 a Scientific American's magazine annual list recognizing 50 outstanding acts of leadership in science and technology. He is the Guinness Book of World Records for the most advanced mini robot for medical use. Please give him a round of applause. He is a member of the Swiss Academy of Engineering and is a foreign member of the Chinese Academy of Sciences. He is on the editorial board of several academic journals, including the founding editorial board of Science Robotics. This is a very, very prestigious robotics journal published by Science Magazine. Please, and through his efforts, we're able to publish there because Brad tell us, guide us as how to, get what we are working on to be at a level that is publishable to Science Robotics. Please give him a round of applause. And an annual, and also the founding editorial board of Annual Review of Controls, Robotics, and Autonomous Systems. I used to joke with Brad to say that if his Navion invention that we will be showing now will eventually be used on humans, he will definitely win a Nobel Prize. Both of us laughed at the idea, but deep inside, I know it is not far-fetched. Ladies and gentlemen, it is with great pride and honor for me to introduce to you our guest speaker today for the topic micro-robot telesurgery for stroke, Professor Dr. Bradley James Nelson from ETH Zurich. Please give him a round of applause.
Okay. Now, got to get everything set up. There's online things, so let me make sure we can get this going here. It might take a couple of minutes to get it going. Let's see. Did I do the right one? What's this? Do we need to change? Do we need to push something here? HDM something? All right, that's on now. Share Microsoft PowerPoint. Okay, I think everything good? Great, okay. Well, thank you very much, everyone, for attending. It's an honor to be here. As Rodrigo said, he said a lot of things about me. Let's see. So I started in the field of robotics a long time ago, and after spending 3 years in it, I came to Botswana and taught at Tutume Makama Community College up in Tutume. And that was really a life-changing event. I was very young then, and I had 2 months of training in Molepolole, learned a little Setswana, learned a lot about the culture, and then found myself posted to a Kalunga region where I had to learn a new language. And so don't expect much from me. I can greet, I can ask you where are you from, and I can nod and smile a lot. That's about it. But when I came here, we really got to know the people, which is of course the greatest part of Botswana. But it's also a fantastic country with a lot of resources, a lot of potential, huge country. And I also met a woman here who changed my life as well. So this is a special place in my heart for this country. And I was excited to learn that there was a science and technology university here, and then I even knew a professor here. So that kind of started me down that road. But even before I came to Botswana, I was thinking about robotics. In 1984, I started as a master's student in Minnesota, working in just traditional robotics doing assembly in factories and classic mechanical engineering kinds of things. And in the 1980s, robotics was very, very popular at the time. It overpromised a lot. Let's see, are we okay on that? But anyway, yeah, if there's some issues or echo online, please somebody let me know. So you might want to turn off your speakers or microphones here too. So, but robotics is very broad. These days, you see a lot of humanoids, like in the lower right corner. You see a lot of drones, like next to it, the Botswana or the Beust vertical takeoff landing. But robotics is a lot more than humanoids. It's very popular right now with NVIDIA, AI, ChatGPT. People think there's going to be a ChatGPT for robotics. I can have a talk with you about that and my opinions. But I've been in the field for over 40 years thinking about it. Started as an assistant professor in Chicago for 3 years, and then Minnesota, where I did my master's degree, actually asked me to come up in 1980. It was a 98, and I did 4 years as an associate professor there. And then I was contacted by a university in Switzerland called ETH Zurich, or the Swiss Federal Institute of Technology Zurich. And they said, we have a position in robotics. We think you might be an interesting fit for that. Can you come out and talk to us? And that was in 2002, I started there. So why would I move from the US to Switzerland? Well, ETH is a very unique university in the world. Founded in 1855, it's really been a driver for Swiss science and technology for the last 170 years now, right? 171 years. Much like BEUST has been and will be for Botswana. The first job we have is educate the scientists and engineers we need in the country. The second job we have is to make sure we are leading the country in the right directions technologically so that we're prepared for the future. So that's why we spend time on things like quantum computing, why we've been in AI for years, we've really built a huge robotics program there for years. And it is always the top-ranked university in continental Europe. It's almost always in the top 10 in the world. It's a place of excellence. But one of the things that's very attractive about it is it gets about $1.5 billion, which is on the order of what, 25 billion pula a year of direct funding. And that money goes to the professors, not just to professors, but that what we are given is enough funds to support a group of about 8 to 10 people without writing a grant. And what that does is give you a lot of freedom, right? It gives you a lot of freedom to pursue the ideas you want. And sometimes these people do incredible things when they have that freedom, that academic freedom to pursue their dreams for research. You might notice some of the people on the bottom there and recognize them. Albert Einstein was a student there and later a professor. My first week at ETH in 2002, Kurt Wüthrich there on the bottom right won a Nobel Prize in chemistry. We have Pritzker winners. These are in architecture. We're our main architecture department in Switzerland. Fields Medal winner, Nicola, who we work with, is on a great trajectory. And so I think that's one of the things that's attractive about that. And so when I came in 2002 and started to realize what that means, I started dreaming bigger about robotics in a way, but smaller in a way too, right? I started thinking, what would be a grand challenge in the field of robotics? And so this is an animation. What I'm going to show you is an animation we made in 2003, where I started thinking, what might we do? What if we could make robots that were small enough to go swim through your bloodstream and be guided or guide themselves to locations throughout your body? 2003 is a long time ago, and we were pretty proud of this animation at the time, and it still doesn't look too bad, but it's, what is it, 23 years old now. We didn't know anything when we made this. What is this really going to do? How is it going to move? What are we going to, what's we going to do? But we had that freedom at ETH to dream big, right? And to think about the future. And so that created a program in my group where we started thinking, what if we could make really small machines? That's just a challenge. It's an intellectual challenge. It's an engineering challenge. It's a scientific challenge. And so over the years, we've been just trying to figure out how to make smarter and more intelligent micro machines. And also thinking what we might do with them. And it's really fascinating. We start going down this path, and as an engineer, your intuition fails you at these scales. We're used to things at human scales, but at small scales, you start to look at nature and you start to think, well, why did like a bacteria like E. coli, these micron or two long organisms, develop this rotary motor, and to allow it to propel itself, which bacteria were first seen in 1675, but it wasn't until 1973 that Howard Berg published a paper that realized they were using a rotary motor to propel themselves. We thought, how as engineers can we build something like that? We weren't sure what they were going to do. We would say, oh, they're going to deliver drugs, but we weren't really sure. It was more of an intellectual challenge. And this is what Rodrigo mentions, the Guinness Book of World Records. This is what they latched onto right away. We first published some of this work in, I think it was 2007 was when we actually first published some of the initial work on this. But that's intellectually just fun, to see how nature works, to understand the mechanisms and think, how can I bring technology, learn those lessons and bring technology to be inspired by that? Coming back to Botswana, one of the things that inspired me is this animal. You see these all the time around here. It's Sibokolodi, I think, is the Tana word. In Kalunga, we say Jongololo. I remember that. How can we make one of these things, right? And it was a fun project. It was kind of one of those, let's do it, let's get the paper out, and let's move on. But we learned a lot of lessons on how to manufacture things at these scales, how to coordinate all these different legs and pairs of sapiens, and understanding how other kind of organisms like Paramecium, how we can use these to drive through. And we learned a lot about what we're using here in magnetic fields, and we hear a lot about magnetic fields. There's an elegance that I think a thrill. But anyway, Botswana is in my blood, as you can see, right? So I still get a thrill every time I'm driving and I see a Sibokolodi across the road. I have to make sure I don't run over it with a car. So another organism that we found interesting was great. What's it called? Another organism is a parasite called Trypanosoma brucei, and it is responsible for trypanosomiasis, or African sleeping sickness. Now, what interested us about this organism, of course, isn't that it creates disease, but how it changes its morphology. How does it change its shape during its life cycle? So at certain certain times in its life cycle, it needs to swim in your bloodstream after you've been bitten by a tsetse fly, so it can swim, and then it's got its long, slender form. And then once it crosses the blood-brain barrier, it just kind of sits there and creates a stumpy form and starts procreating. And eventually, of course, the patient, the host, gets African sleeping sickness, and eventually dies, a horrible disease. But we were interested in, can we make a robot that there's my cursor, that can change its shape. And so we learned a lot about working with polymers, and how we can incorporate, in this case, we incorporated graphene, and graphene absorbs light and heats up. And that little temperature change can cause changes in the shapes of the polymers, so that we can move from swimming kinds of devices to the stumpy kind of eluding kind of device. And so, these things are interesting to do, but then, at some point I'm an engineer and I really want to, get my work out. I don't want to just publish papers. I want to try to see how we can translate this out. And so we started getting more serious about thinking about drug delivery. Why would we want to use microrobots to deliver drugs? What would be the benefit of that? Well, it turns out there's a Swiss connection to that. About 30 kilometers from my lab, there's a little town village called Einsiedeln, and this person grew up there who, by the name of Paracelsus, about 500 500 years ago or so. Paracelsus became a doctor. At this time, being a doctor was kind of a strange thing. We had 4 body humors, and their job was to try to balance these body humors. But in the late 1400s, early 1500s, syphilis invaded Europe, and it was a deadly disease. They were having no success in treating it. But Paracelsus realized mercury salts could treat syphilis. But he also realized if you didn't give enough, nothing happened. If you gave too much, it would kill the patient. You had to give the right amount. And he has this phrase, only the dose makes the poison. Everything's poisonous if you give too much, right? And that was kind of an insight that was very new if you go back to that time frame. And so he's known as the father of toxicity. And what he's talking about is this idea of a therapeutic window, that when you deliver a drug, you need to deliver the right amount, not too much and not too little. And sometimes for certain diseases and certain drugs, those windows shrink and become very small. Now, it turns out last year, the pharmaceutical industry spent about $250 billion on developing new drugs. And about 90% of those developments are going to fail. And about 30% of those failures are because the drugs are just too toxic to the patient. They can't deal with that. And so the idea of microrobots is maybe there's a way, instead of doing systemic delivery, that we can actually do a targeted delivery. And that's what this little animation shows. Now, if you have something like, some diseases, you need a systemic delivery. But a lot of diseases, particularly brain cancers or tumors, these kinds of things, blood clots, are very localized. And so if you can target those, you can give a much higher dose, but it will have much lower effect. And so that then brings us back to microrobots. Can they carry drugs, and can we deliver something interesting that can help the patient? So then the first question we thought about in 2003 and working on microrobots was, how are you going to make them move? For us, we've stuck over the last 23 years now with the idea of using magnetic fields. So we embed magnetic material in our devices, and then we drive them with fields. And just, I'm going to give you just some basic physics here, but if you put a magnetic material in a field, it will align its easy axis, its long axis with that field, like a compass needle does. If you're looking at a compass, it always aligns with the Earth's field. The other is with gradients. If the field gets stronger, then we can generate forces. We first use these at microscales to mimic bacteria and the way they swim. On the bottom right there, that's a macrophage, that cell. And what we have is a little microrobot that's disguised as a bad bacteria, and that macrophage is trying to eat it, like it does when bad things invade your body. It's part of your immune system. And it allows us to understand then the mechanics of how do these devices get engulfed and these kinds of things. So over the last couple decades, we've developed a lot of expertise in how do you generate these magnetic fields? How do we generate these these field lines, these yellow, kind of yellowish lines there? And it turns out that's a purely robotics problem. So if you're controlling a robot arm or a robot leg or something, you've got all these motors, and you need to coordinate all those motors to get the kind of motion you want. And that's what roboticists are really good at. But it turns out with our electromagnets, and these are magnets we can put current through to generate these fields, it's a very similar problem. We have several different electromagnets. We generate currents in each one of those, and those generate then a field or a field gradient of different kinds of fields in the workspace, the area of the robot. And that was some insight that my group had some years ago on that. And that allowed us to be one of the first to we were the first to demonstrate how we can move small devices very, very precisely within the body. And that took us a long time to figure out how to do. We published very few papers on it. But again, this is one of the joys of working at ETH. I don't have to publish if I don't need to. I only publish when I think I've got something important to say, right? And I think that's allowed us to spend a lot of resources on something that gives us a real advantage on this. Now, if I think about moving my microrobots from my lab into the hospital to actually treat patients, there's actually a lot of pieces of the puzzle that have to come together. We have to think of many different aspects. How do we make them move? How do we see them? What are they going to do? And how do we make sure they do what we want them to at the right place? So we think about them like that. We have to think about, are we going to take them out or can we leave them in the body? Those are other things that we need to think about. And we prefer leaving them in the body, but that reduces the amount, kinds of materials we can use. We can't use things, there's three elements that are magnetic: cobalt, nickel, and iron. Cobalt and nickel, you don't want to leave in your body, but iron's okay. Okay. So we think about that, but then also other parts of it. Then we also have to think about federal the regulations like the FDA in the US. What kinds of materials could we get through that process and are reasonable to choose from? And the other thing is it takes a lot of money to do this. And so we need to also think about return on investment. Are we really going to make an impact with that research? And so we need to think about the economic viability of it. And so what we've come up with is this little capsule, and I'll be talking about it. But it looks about like a peppercorn, but it has a lot in it. It's got a drug, it's got the magnetic particles in it, it's got something that allows us to see it, as well as then the binding matrix that puts it all together. So the first thing we think about is how we make it move, and that's what the iron does, iron particles in it. And then we take what we saw as a Navion, this magnetic system, and we take two of those and we put them by the patient. In this case, we're doing procedures in the brain of the patient. So we put those there. And then we build, the way we approach this then is we build plastic models, we 3D print models of the human neurovascular structure. And you'll see some of these over here when you see the demo later. You'll see some of the small pieces of those, but these are from preoperative images, magnetic resonance and CT images from patients. And then we can, try to control the directions these things move as they go through this network in our brain that's delivering blood throughout our brain very, very, very nicely. And there's a lot of blood flow. The blood flows through the brain in places at about 40 centimeters a second. That's super fast. And so we got to think a lot about the physics. We got to think a lot about all the procedures there. So what this is going to show is a little one of my little capsules entering the bloodstream. And I have a whole group of chemists led by my co-director, who's a chemist, Salvador Pani. And you see that's actually slowed down by a factor of 5. But we're constantly adjusting the fields and moving that through that network. And we can select what part of the brain, what part of the neurovascular network do we want that to go to. So that's navigating, how we can move through the brain. The other thing is how we can see it, and you got to see it. You got to know where it is. And this is a huge challenge, to look into your brain and find something, especially when it's moving that fast. So we spent a lot of time developing the chemistries, the right materials so that they show up really nicely in an X-ray images. So there's some PhDs, several PhDs in that alone, right? And how to do that. And then how do you trigger the functionality? Well, it turns out with some of these magnetic particles, if you oscillate them, the one on the left you see that little dot, that's the peppercorn capsule. And on the right, it's dissolved, and then the drug has diffused in the whole container. And so we've started that. And then what are they going to do? I'm going to talk about stroke, and I'll talk more about stroke, but here's an example of a cerebral artery that's a human thrombus, a human blood clot that's been introduced into it. My students actually donate blood for their work, so to create those human blood clots. And so we can drive this through there, and then we start to dissolve it, and you see the timer, it takes some minutes, but that's okay. And eventually starts dissolving that blood clot and shows how we can cause this to move through. So this is an example of delivery of a therapeutic agent. Now, what we're delivering is a drug called tissue plasminogen activator. We're delivering about 7,000 times less than you normally would for a patient. The way this happens right now is if you went in and you just had a stroke, they would figure out how much you weigh. They would say, oh, we do about 72, we do about 1 milligram per kilogram that you weigh. And we just hope a little bit of it gets there to dissolve it. But in our case, we can reduce that dosage by 7,000. And TPA actually has a lot of bad side effects for several patients. And so, again, that toxicity issue is being dealt with right here. So that's the idea of these devices. You've got to put a lot of functionality, a lot of chemistry, a lot of mechanical engineering and physics into them to get them all to work. But then you got to make sure they really do work. And the way you do that is by animals, animals, animals. You do as much as you can in 3D printed devices. But it's not just doing the animal experiments. These start early in the day. We take the animal, we do an MR on the animal, so we know what its brain and the neurovascular structures look like. And so we can develop a 3D model of that. Then we put the device into the animal. We figure out where it is. We control it. And then from that 3D model, we navigate it. They stuck a picture of me. I guess I'm the one directing the navigation there. But then we go back to that 3D model and we actually 3D print the real vascular structure of the animal we just did. And we go back and retest that in vitro or, in the lab to make sure we understood exactly what happened in that case. So it's not just sticking these things in and making them work. It's really understanding. Around 50, 60 kilograms in size. Those are two of our Navions, and then a fluoroscope above the kind of yellowish thing there. And then the first thing we do is you build a roadmap in vivo at the vascular structure of the pig by putting a contrast agent in. You'll see a little white, looks like a roadmap, like you'd see in Google Maps or something. And that tells the surgeon where you want to go. We deliver the capsule through a catheter deep into the brain of the pig. Inspired by things like bacteria, certain nutrophages that are in our bloodstream, with gradients and start to move these things through. First is move that a little bit, and there's people can have there's basically two types of stroke that people can have. There's hemorrhagic stroke where a blood vessel bursts, but about 87% are strokes are that are in the brain where that's kind of a representation at scale. These little pink thing. This is what a blood clot is like in your brain. It's just a little hunk of blood that has coagulated. Usually that's what it is anyway. And it's the second leading cause of death in the world that these things get there. It's a huge issue in every part of the world, and treating people is important to do that. I mentioned there are enzymes that can dissolve that, but the real standard of care is what's called a mechanical thrombectomy, where they actually insert a wire into your femoral artery. They snake the wire all the way up into your brain. And then once they reach where that blood clot is that they can see in an x-ray, then they'll put a catheter over that to try to suck out the blood clot and remove it. It's the best way, and it's been about 15, 20 years ago, the idea came to surgeons it might work. And 10 years ago, there was a study that showed this is the best thing you can do if you have a stroke, is get in there and get that blood clot out as soon as possible. The problem with this is the actuator, the surgeon's hands are about 1 meter or 1.5 meters away from where they're actually controlling it. That's a super hard, that's and what we realized as we were working on our micro robots is that our magnetic fields are actually well suited to helping guide the tip of that. About that in a little bit, but I want to talk a little bit more about stroke. So turns out 1 in 4 people, so that's a lot of people in this room. If you look around, count 4 people, and one of you is going to have a stroke, right? the outcome isn't good. About half of the people who have strokes die, and about half of the people who live suffer permanent disabilities. So 77% of people suffer permanent disabilities. Now, I said that mechanical thrombectomy is the standard of care, but around the world, less than 3% of the people are getting that procedure. Even in first-class medical places like Switzerland and the US, it's still difficult to get patients in and get them treated because you've got to get to a center that can do that. You look at this map, this is travel time to healthcare. You can look, light is good, dark is bad, and you can look down in Botswana and you'll see, yeah, it's not surprisingly, it takes, if you're in the middle of Botswana, it can take a while to get to healthcare, and let alone to a place that can do treat a stroke, right? So it's a lot of people just simply don't have timely access to the healthcare they need. And the thing that I haven't emphasized enough is that time is brain. So we know that if you have a heart attack, which is also a vascular disease, or you have a stroke, you've got to get to a hospital as soon as possible. So again, go to the Botswana government webpage and they'll tell you the symptoms of stroke. There's an acronym FAST. It's or speech slurs. The T stands for time. Face, arm, speech, time. That means get to a clinic. It's been shown that if you can get treated within 2.5 hours, 150 minutes of the onset of those symptoms, you have a 90% chance of being functionally independent when you leave the clinic. But that's a short window. And if you're in the middle of CKGR, that can be a problem, right? Or somewhere. If you're in the mountains in Switzerland and it's a cloudy day and the helicopters can't fly, that's a problem, right? And so we know these treatments work, but we're having trouble getting them to people because keeping a stroke center going is expensive. You got to keep a staff going 24 hours a day, 7 days, 24 hours a day, 7 days a week. Specialists and hospital setups are required, and it's just not available to most of the world. And so we've been looking at new technologies, and a number of other groups and companies are looking at how we can create simple, scalable technologies built on existing infrastructure. I was in Ghana recently. 31 million people. Stroke is the leading cause of death. There's one doctor in the whole country that can do a mechanical thrombectomy. And it's just simply not possible to get to some of these places. And so, as I mentioned, we realized that the same device we're using to control microrobots can also be used to control these little wires that are going deep into your brain. These wires are on the order of less than a millimeter, 0.5 millimeter in diameter. And if you put a little magnet on the tip of those, you can guide those wires, and it's a much easier procedure. And you'll see this later when Lucky connects to my group back in Zurich, how much easier it is to do this. These surgeons typically train for years to do this procedure, but you can pick this up pretty quickly with the system we have here. In fact, you control it with a PlayStation controller, so it's like playing a video game. But there's more technology developments that make this even more exciting. Since it is easy to control, it's easy to do from a telesurgery standpoint. Here. Am I still on my, seems like my, I think the online link seemed to have died on me, but I think we're back now. So we've done some experiments. This is with Dr. Bendock in Phoenix, Arizona at the Mayo Clinic. And he's connecting one of our devices. This is kilometers away from Zurich. And this is the first time anybody ever developed this. You'll here in the lower right, well, the middle image, let's see when we get there. There's the guide wire going into the vascular structure. And then that green there is the that represents an artificial thrombus, an artificial blood clot. Guide wire comes there, and then he puts a catheter over that. So that has a tube in it. That catheter is about 2 millimeters in diameter. And then he pulls the guide wire out, sucks the blood clot out. Now we also we've demonstrated this also in animal models. This is the first one where we did a pig. This is in at the University of Zurich. That's the roadmap of the pig. That arrow pointed to the blood clot where the blood stops. And now the surgeons are controlling this remotely here. Putting the guide wire in, and then the 0.035 inch is about 800, 900 microns. And you see the surgeons just playing a video game or something. And now the catheter, in this case, the pump has to be reconnected. We hadn't automated everything yet. And then they just put a little on the catheter, pull the blood clot out, and then the blood flow is restored. And then finally, this is one where we had the pig in Bern, Switzerland, the capital of Switzerland. We had surgeons, neurosurgeons in Zurich. That's Tillman Schubert. That's Dr. Bendock again. He's in Arizona, 9,300 kilometers away. Zurich's only about an hour from Bern by train. And so then this is in the pig. This is the guide wire going in, being guided magnetically and steered. There's the blood clot where the arrow is. Controlling the procedure through the clot, and then they put what they call a 6 French catheter, which is the same as 2 millimeter diameter catheter over that. They pull the guide wire out, catheter still in place, and then again show this. Now it looks simple, and that's good, but a guy like Dr. Bendock or Tillman Schubert, they spent years and years and years figuring out how to do this by hand and understanding the needs for it. And with about 30 minutes of training, they're able to do the same thing with our system. So we find that quite gratifying. Now, the thing about the system is it can be made portable. And so we think one of the future technologies this or more complicated procedures being done. And so we were particularly excited to see, sorry, we're but we were, excited to have a paper appear in November in Science that represents about 23 years of work in my group. And it's gotten a lot of publicity, a lot of press in Science magazine. Of course, it's one of the top science journals in the world. And I think according to their statistics, this paper is one of their top 3% in terms of publicity and excitement that it's generated around the world, because it's the first time anybody's shown at human scales that we can deliver drugs at clinical scale within the human body and showing a complete pathway for that. So the next step now is to the regulatory process and look at different kinds of diseases that we can do for that. And so I want to kind of close with this little video, this animation we made. So think back to my animation from 2003. This is from 22 years later. It shows a patient with blood clot. And then what you see here is what a systemic liver, where the drug is going everywhere. But we can actually, it's very okay. This is our microrobot, you might call it, or capsule. And it has a very specific chemistry to it. We have specific catheters that can release these devices, guide them through exactly to where we want, the precise locations in the human brain, dissolve them, and release whatever drug you want. And in this case, try to dissolve a blood clot or perhaps some type of a tumor, anti-tumor drug in those locations. So that kind of represents to me a couple decades of work that I was quite happy that we got out. So I'm going to leave it right there. I want to thank you very much for your attention and for being such a nice audience. Thank you very much.
Thank you very much, Professor Nelson, for your comprehensive and innovative presentation. For sure, our audience have learned a lot from the presentation and realized the urgency and the importance of the technology that developed in solving the problem that we have all over the world. A big round of applause to Professor Nelson. At this moment, ladies and gentlemen, you are welcome to give comments, impressions, or questions to Professor Nelson. Please identify yourself before you give your comments or reactions. For our online participants, you're also welcome to give comments. You can use the chat box or in the zones. Okay, so anyone who is wants to give comments, Professor Nelson will be here ready to answer whatever comments or reactions these have on his observation. Sir?
Was introduced earlier, seeking just a question. I want to understand what the process. So you had the image of the blood vessels in the brain, which was in red and those. And then when the micro robot goes through, at that point, is it live? Is it an image you take beforehand? Was it a live image as you're navigating the micro robot through the brain?
Yeah, that's a good question. Those are live images. So these are live X-ray images. So this is a fluoroscope. Normally they do 30 frames a second or less. In this case, we do 60 frames. So we capture very with image processing, and from that, then we can guide it, and we say, oh, exert the field this way, exert the field that way to keep it there. So, and that's one of the challenges is actually being able to see this in real time to make sure it actually goes where you think it's going. So,
thank you. Very inspiring. Thank you.
Thank you, Rob. Thank you, sir. Anyone wants to give questions from our guests, from our students? Yes. We have gentlemen here. Please identify yourself.
Good morning. My name is Tumisan Makongo. I'm a student here at East. Protocol is first of all, I just want to say that this is some really good work. It's very inspiring to see such groundbreaking and very innovative work being done. I fell in love with some of your work, and I wanted to ask that what does a student like me or students like us have to do to get the opportunity to maybe work with you and get some scholarships? So, yeah, let's see.
I think that's a very fair question. So, yeah, it's a challenge. I mean, I get several emails a day from students all over the world wanting to come to our lab. So it's the competition is stiff. So, but there's a couple things you can do. Lucky, we got to know Lucky when we came down here. Lucky came up to Zurich. We got a chance to work with him. My group got a chance to know who he was, the kind of person he was. We knew he was technically competent. We knew he was a good team player, an easy guy to get along with, right? And you know, it's hard whenever I hiring people on paper. So it always helps. It always helps if we have a relationship somehow with the person, so we know who they are, or if they come from somebody who I really trust, who highly recommends and says, "Oh, this is the best student I've had in 10 years." So that helps a lot. The other thing is when I hire a student at ETH, I have to find we pay a good salary, and so I have to make sure I have set aside funds to get the student through that PhD. And there are scholarships and fellowships available. If you can bring your own money, that makes you much more attractive to me. So I don't have to go searching for money. I mean, I do it all the time, but it also makes it easier. But I think, you know, it's good to get your foot in the door somehow in these groups, especially, I mean, you know, Boost is a new university, you know, in the scheme of it. And so a lot of people aren't sure about it. But, you know, as you get people like Lucky out there and people are, you know, he sets a good example then. And people are like, oh, yeah, oh, this guy's good. Maybe other people are good too from there. So these things help.
Okay, thank you very much. And yeah, Lucky, thank you for bringing me us to PPS. Keep the job going and hopefully you will not fail. But I'm sure I've achieved as well as we have lady. Anybody wants to give a comment?
Good morning.
Morning.
Protocol observed. I think I'm fortunate that I just completed the course for mediate. I think a month ago. Right? So I just wanted to ask on the same thing on the field robotics, right? I know from our ancestral robots, the micro and the macro world, we do have perception, we have them control from motors and all that, right? But according to your evidence for how you can project things, you see us having to achieve like things like sensing and perception, having a power on board in this network control as well.
Okay, that's very nice question. So we created a MOOC, an online course, and that's the course you took. That's right? Is that right? Yeah. I'm glad you took it. Okay, I don't know how many people are taking it. I don't keep track. So so I do see these devices getting more and more intelligent, and you're starting to see some of people actually including silicon in them and dissolvable structures, and that's also coming out of some of the work in wearable computing. And so we can see now logic in the future, maybe on some of these. Whenever you talk to a surgeon, what they really want to do is see inside. They really want little cameras that can look and see these things. And so I think we're going in that direction. But right now, we're just trying to, you know, we're looking at something that we think we can get out in 3 to 5 years, right, into that. But I think in the future, it's going to go the way you mentioned. So yeah.
Awesome.
Thank you. Another questions here from our student participant.
Good morning, everyone. My name is Bukani. I'm studying here at chemistry. So I have a question concerning the chat that you might have faced in developing this sort of structure. And also just to ask, I'd like to say 2 questions. I don't really understand the scale at which this is at, so I will ask to say, I would like to believe that some of the challenges that you may face in this would be, I don't know, rupturing an artery. I mean, you're controlling these things magnetically, right? So how often does it happen that you more or less like rupture an artery while you're navigating through the arteries? And also when it comes down to mechanical thrombectomy.
Mhm.
I'd like to understand when it comes to thrombus, the clot, you say a catheter sucks the clot out. So are there different varying degrees to which the clot will advance? Because I know what a clot looks like when I have cut in my hand, right? It's a small mass. So I find it really hard to visualize it being able to suck and also having a very narrow diameter. So yeah, that's my question to you.
Okay, great. No, two very good questions. So the first was about rupturing vessels, and of course that's a huge concern. The surgeons, that's why they train so long to do this, because if they do rupture vegetable, it's a bad outcome for the patient. And so we always have to make sure that the forces exerted are within that framework. And so we do tests, like on placentas. We get placentas from the women's hospital and do tests on those blood vessels, and then we do histology to see, did we create any trauma internally to those. So we're very careful about that. That's part of the regulatory process. The other question you had was on the mechanical thrombectomy. Yeah, you're exactly right. Different blood clots have different mechanical properties depending on how long they've been in the body and how big they are. And so I talked about aspiration and sucking it out, but there's another approach called a stent retriever. They go through and then they have a little wire net and they drag it out with that net. That's another procedure. But these are the challenges. This is what the medical device industry works on is ways to do that. And so, but there's still a lot to be understood about the physics, the material properties of these, and people are always thinking of new ideas, but to actually get them into the clinics is a huge challenge, because you have to make sure it's completely safe and not below the current standard of care. That's one of the challenges.
Okay, thank you. We have one question from our online participant. It will be read by Mr. Now.
Thank you. This is a question from online platform.
Okay.
Given the non-linear environment of blood vessels, how do you model and guarantee robust stability margins?
Robustness of motion through the arteries, I guess, is probably the
Guarantee robust stability margins.
robust stability margins. Yeah. Okay, I see. That's where a lot, read the paper. So that's where a lot of the heavy lifting in the paper is understanding what the fluid flow is, and doing it in vivo, then taking that 3D model we built of the pig or the sheep that we're doing, 3D printing it, and then going through and making sure we understood all the physics of that. But robust stability margins, that's one of the reasons, the question earlier about the feedback from the fluoroscope, from the x-rays, there were 60 hertz feedback. And so by getting fast feedback, we also can guarantee more robustness that way. But yeah, there are a lot of interesting control problems, and the control community is starting to look at this in more detail. So I think this is a good problem for somebody to work on in that area.
Thank you, Professor Nelson. I still have one comments from the student.
Good morning, everyone. My name is Mbako. I am supervised by Professor Masolo. I'm a master's student here. I'm one of the students working on the mini Navion. My question is regarding the catheter movements. Is it possible to track the catheter using ultrasound as a potentially safer method, contrast to the hours of exposure to the X-ray?
Yeah. I think that's a great idea. X-rays, of course, are harmful, and you don't want to expose people to too much. However, for patients, they're not so concerned because it's just one dose. You're in there. The real concern is for the surgeons. They're standing next to the patient and they're inundated with this. And so I know I work with electrophysiologists to do this similar procedures. If you're an electrophysiologist, they've done a study of electrophysiologists who have brain tumors. 85% are on the left side of their brain. Well, that happens to be where they're closest to the fluoroscope. So I think it's really the staff that's in more danger, and that's the advantage of the remote procedure. They can do this from meters or kilometers away. But it isn't, we don't want to expose patients to x-rays if you don't need to. but we also, realize as you're going through the regulatory process, you don't want to change things too much. If you change too many things, it becomes a mess. So you want to just kind of have a slow strategy. They're very used to X-rays, fluoroscopy. We just want to make small changes. And so, but I think that these are great research topics for people to think about, because this is where the future will go at some point, I think.
Thank you, Professor. We have other questions here from the on-site participant.
All right.
Thank you. My name is Nelja from the research office. I'm not a scientist. So I wanted to understand in a nutshell, where are we right now with the technique? Taking it from in Botswana, what can I tell my mother at home about the take home from this making? And lastly, I've seen that you've invested a lot of time in doing the research. I wanted to know whether the technique only addresses the issues of stroke. Can't you tweak it somewhere maybe target cancer, breast cancer, issues and other diseases? Given the amount of time that you invested in the technique, can you take the design somewhere to address
Yeah.
Thank you.
Thank you. Yeah, two excellent points. So where is the technique in Botswana? I'm not sure what all the capabilities are, but if you do have a stroke center, it would have to be in Gaborone. I'm not sure what Francistown can do. They can administer TPA to try to dissolve it, but you need to get there quick enough for that to be effective. And that's where we think, I showed the picture of the Land Cruiser. That's where we think we can have portable systems where if you can get to a remote clinic or get a message to a remote clinic, they can come and deliver to you more quickly. That's what we're hoping for the future. But right now, the first thing is recognizing what you have, then trying to stabilize the patient, and then getting to a clinic where they can deal with you as quick as possible. In Zurich or in larger population centers like Joburg or Cape Town or somewhere, there will be centers you can go to. I was down in South Africa at a private hospital in Stellenbosch. There was a stroke center 30 minutes away from them, so they just put the patient in the ambulance. But he says, the problem I have is when I'm 400 kilometers away, you might be lucky on the day and a surgeon's there who can do the procedure, but there's no set 24-hour, 7-day-a-week stroke center. And that's true in a huge part of the world. So that's why we think this telesurgery is going to be so important. And then the second part of the question was, let's see. Can you remind me what the second was?
Application to other diseases.
Oh, application to other diseases, that's right. Actually, we have a project right now going on where we're looking at brainstem gliomas. Gliomas are these terrible aggressive brain cancers where we're trying to deliver the drug directly to there for this. The other thing, I had a slide I took out here where we can actually take small endoscopes. So a lot of people suffer stomach problems. Over 1 million people a year die from gastrointestinal diseases. They're not getting diagnosed enough, for instance, in your stomach, because it's a difficult procedure. You got to put the patient under, you put a centimeter and a half endoscope down the throat of the patient, and people just don't like it. It's difficult. But we have a little 4.5 millimeter diameter endoscope you put in your nose that can go into your stomach and do a scan without any anesthesia. It's just very easy to do, and it can even be done remotely. We controlled from Zurich a device in a pig in Hong Kong last year. To demonstrate that. And so this technology, we think, has a lot more potential than what you're just showing right here. And I think gastrointestinal diseases are also huge, have a huge mortality. And so we can do a lot more diagnosis. So imagine you go to a clinic in Tutume and you want to do a scan. Well, they need to send you to Francistown. They do have endoscopes there. Last time I was there, they were all broken, but they do have them. Or you could maybe have one of these devices in Tutume, and a surgeon in Francistown or Gaborone could just get online and look and do a little scan and say, oh, you're okay. Oh, let's do a biopsy, take a biopsy. Let's wait and see what the result is. Otherwise, right now, a lot of times it just doesn't happen because it's just too hard. And so we think we can make these procedures easier. So there's a lot more we can do, but I've only got so many hours in the day. So thank you.
Thank you, Bro. Any questions or questions here?
Are you guys ready for your? Yes, sir.
Good morning, to all of them. My name is Robert Dane, currently studying bachelor's. So I have two questions.
Mhm.
The first is, do you see this technology potentially being used within other fields, other sectors, and the sciences? Second question, I'm interested in work. Hopefully, I could branch out into something what you're doing. I was wondering how can I give access to research?
Okay, thanks. So first, other areas, I've got a couple good students who've been working on these magnetic field generation and looking at dynamics, that is time varying aspects of that. And they've been contacted by people in fusion energy. So a lot of these fusion tokamaks use magnetic fields to contain the plasma. And so they're very interested in our work on how we model this and how we can control devices inside of the tokamaks and actually maybe levitate devices within them to inspect them. So there's some areas there where there's already some interest from outside. We've also used some of this technology can lend itself to environmental cleanup as well. I didn't get into the materials aspects, but there's ways we can get rid of toxins this way. There's a spinoff out of my group doing that. And then how do you get into the group? Yeah, I mean, I think the thing is, you work hard. You want to, I think there's one thing I always did in my career, probably, I don't know why I did it, but it was a good idea. And that was whenever I did something, I made sure I had something at the end to show for it. I didn't just do it. I did it because I loved it and it was fun, but I also made sure I had a paper, a poster, a presentation, something to put on my resume to show a result. After you do that for a few years, all of a sudden you've got an impressive looking resume. But the important thing is, and I always tell my grad students this, right? The most important thing a grad student learns is how to set their own goals and how to make sure those goals are achieved. Because I don't stand over my students with a stick and beat them until they get a result. It's like it's up to you. And I think setting your own goals, getting a result, and something that you can communicate and show, hey, look what I did. I think that's it's just something, I don't know. I just always did it during my PhD. I just made sure every 6 months, no matter what, I got a small paper out somewhere. It kind of adds up. It takes time, but it's kind of the tortoise and the hare, right? Yeah.
Thank you, Professor. Thank you, Professor Nelson, for that very sound advice for students. Professor Nelson came to this stage here not just by sleeping and drinking stuff workouts, right? So there's another question from our online participant. Nashi. And yes, I'm sorry. Okay, just introduce yourself before you.
Okay, hi everybody, I'm Nyasha. So our question online says, thank you, Professor Brad, for a great presentation once again. I wanted to ask, in a magnetically guided microrobot telesurgery, what are the main control and sensing limitations, and how do you see machine learning and AI contributing to robust navigation? The second question from the same participant was, also, apart from stroke treatment, are there other applications, medical and not, of this technology, which I think has been covered?
Okay, yeah. Yeah, the physics of this I didn't get into. The problem with magnets is that the fields drop off with a cube of distance. So if I go from 1 centimeter away from the magnet to 10 centimeters away, that means the field dropped off by a factor of 1,000. And that's a big deal. That's hard. The other thing is we know the physics, but doing really accurate models is challenging. And so AI can contribute by learning how each of these coils generates the field and the gradient, because there's a lot of interactions. Some of the magnetic flux is influenced by other electromagnets, and it becomes, while we know the models, it's really difficult to do a good model of that, but learning can be used for that very, very well. Similarly, in guiding these procedures, I think it's wide open, and there's a lot of people that are looking at it. And a lot of people, the US has just started a program called ARPA-H last year. And a lot of their focus is on making these procedures autonomous. That is, you push a button and the device goes in and pulls out the blood clot, right? I think that's a little far out, and I don't think that's probably where we're going to go, but we're going to learn a lot by doing that, by making these procedures automatic, or seeing if we can. And AI has a huge role to play there in the image understanding, and looking at the control. The problem is getting the training sets, the training data that these learning devices need. NVIDIA will tell you, oh, we're going to model it all and we'll learn from the models. No way, that's not going to work. But that helps them sell the hardware, right? I think we still need engineers who do real models. It's not all learning, right? And so we still need to do real physics. So.
Thank you, Professor. There's one other question, please.
Thank you. Good morning, everyone. My name is Kele. So I'm a student under Problem Solar Lab, doing PhD. So my question is, earlier on, I heard you saying that you can this technology can replace the endoscopes. So I believe also the colonoscopes and things like that. So, and we were talking of getting the biopsy from the body, the person. So I was wondering if have you also considered doing, because to get the biopsy, I believe this robots will need to be more than one. So have you considered cooperative control of maybe the other one being to handle the cutting of the biopsy, or can you do everything at once? Thank you, sir.
So if you're going to do a biopsy in like the colon or the stomach or the esophagus, you can do that with a single device. It has a working channel, and you put a little wire in there that's a millimeter or 1.2 millimeters, depending, that has little pinchers, and you can pull it out that way. So that's one way to do it. We did develop a 2-arm procedure device just to see how small we could make it. So we've thought about it, but I think there's a lot of work to do. So I'm not even sure we've published any of that work yet, but I think these are directions, and yeah, I think there's a lot to do. There's a lot to do. So it's an interesting area. All right.
Any other questions? Yes, sir.
Morning, everybody. First of all, sir, my name is Joe Vista. I'm a top as an engineer. You mentioned that those endoscopes are broken wherever in Pakistan. So for me, being as a maintenance engineer, I know doctors are having innovation and trying to get this thing done. But basically, you rely on engineers to make sure that those equipment work as well. Are you also training people, engineers, to work with you with this particular field? Thank you.
Yeah, I mean, I think we try to think through as much of the surgical workflow and procedure as you can. When I talked about those endoscopes, and I mentioned when I was in the Francistown Hospital, they had endoscopes, but they were all broken right at the time. One of the problems with these endoscopes, the big, you talk to the gastroenterologist, the head of these departments, is well, maintaining them, but then you have to send them to the manufacturer because they have to be done to very clear specs, and that's expensive. The other thing is sterilization, and that is also a big problem. I know the head of gastroenterology at Bern told me about 25% of his brain is focused on sterilizing his endoscopes for his department, which is unfortunate. So there are, one of the advantages of this approach that we're looking at, where we can take these, centimeter devices and make them a third of that size or so, is we can actually perhaps make them disposable. So they could be one-shot devices. We might make them cheap enough that you can use them once and either throw them away or send them back to the manufacturer to be reworked and sent back. And so that's one of the approaches in dealing with that. But that's certainly what you got to think about, especially in low resource settings where you can't afford, the high expense of a US system for healthcare. So, but you got to think about that. And that goes into the business model, right? Of if you're going to really commercialize this and push it out. And we try to think that early on. We try to think of that early on. If we develop a device, I have my students design a device where we think, well, wait, there's no way this is going to be made cheap enough to be competitive, or there's no way this is going to be accepted because of some user issue. Those are things that when you work in this area of research that you should think up early instead of coming up with a crazy idea. So, but it's good to have I always like to have real engineers who bring everybody down to earth, right? And say, look, here's the real problems we got to deal with. Can we solve these, as well as the nice, crazy science stuff?
Thank you, Professor. Just one question from the benefits, for the benefits of our medical practitioners, what would be the cost of investment if this technology would be ready for adaptation in Botswana, in an estimate for that one? That will give us idea how
Yeah.
much we have to raise before we would be able to adapt and use this very good technology.
Yeah, I mean, so I've been down to South Africa, talked to, local clinics about, putting a device in and doing things. The first thing you go to these clinics, a lot of these clinics don't even have a fluoroscope to start with, right? To look in, you need a fluoroscope. And so that's one of the first things we want is we want to bring in device. If we're going to work with some of these, we bring in devices that are going to stay and help, so you break your arm, you've got somebody that can, take an x-ray of it. But in terms of the cost of the like the Navion, I mean, I know what the cost of goods are for that, and it's also manufactured by very highly paid Swiss engineers. Now, if we want to move that to China, to Shenzhen or somewhere, we can really lower the cost of that. So I think the costs are going to be reasonable for what a local clinic in Botswana would expect to pay. I hate to put a number because my CEO of the company that's trying to commercialize it will not be happy when he hears it. But I don't think it's unreasonable. There's nothing inherently expensive. It's not like we have superconducting material or any of these kinds of things in it. So I think it can be reasonably costed on, I think so.
Okay, thank you, Professor Nelson, for indulging those queries. We still have two more. I thought we're done. Okay, just these two questions from Dr. Maniwa.
Greetings to everyone, all protocol observed. I'm Dr. Trust Maniwa, product of Prof Ultra. My question will be on the cost of creating that micro robot that you do. How much does it cost? And probably, do you have a sample that maybe you can see through a naked eye or something that you can see through a naked eye? Thank you, Prof.
I didn't bring any of the capsules with me. I do have a blood clot with me, or a simulated blood clot. So I think these I don't think cost is going to be an issue for these. These are made with a high throughput kind of fabrication procedure. We haven't looked at the long-term cost, but if you can, but we've had certainly interest in pharmaceutical companies on this, so I'm not overly concerned about the cost of it. I've had people have compared it to a grain of sand. And other people have compared it to a small peppercorn. So that's kind of what it looks like. It looks like a black dot, but there's a lot in that black dot. So, but yeah, I should have a something like this with these in it that I can jiggle. But yeah, I think cost is. I'm not overly concerned about that. I'm more concerned about the infrastructure costs and trying to bring that down. So.
Thank you, Prof. We have last question here.
Yes, of course. Good morning, everyone. Observed. My name is Andres. Basically, income meeting. But my question is primarily more to the medical side of things. I'm wondering, can this technology work in both types of strokes? Because as far as I'm concerned, I think there's about 2 types. Maybe you could help more on these specific things.
Right, yeah. So 87% of strokes are from blood clots, and the other about 13% or so are hemorrhagic. So this is where the blood vessel bursts, or you've got an aneurysm, which is a little ball that forms, and then that bursts. Now, if you're lucky, somehow they've figured out the surgeons figure out that you have one of these aneurysms that might burst, and they do that from maybe they happen to do a scan of your brain and see it, or maybe it's inherited in your family. And so there are ways that they can keep that from bursting by putting a little platinum wire inside of it or clipping it from the outside. They open up your skull and clip it, but they put a platinum wire. We think our procedure can help with the placement of that wire in it. And there are some of these aneurysms I'm talking about that are very difficult for surgeons to get to, basal aneurysms deep in your brain. And so that's where a lot of the interest comes from surgeons is, can you help us treat these patients, because we really hesitate to do it because one wrong move and you break it. Can our system help with that? And you see these models over here. these little plastic models. That's a company, a spinoff from my group called Swiss Vascular makes those. We've got surgeons who are actually sending us patient data who have these kinds of problems with aneurysms, asking us to print those out in 3D, and then we send them to them so that they can practice the motions and how they're going to look at it, and they can really get a good sense of it and what kind of pushing strategies they can to get to it. And so they'll pay a fair amount for these things to help them. So because these are problems, and we think our system can help, and that's Dr. Van Dock is working with us that I showed earlier on these kinds of things. So great, good question. Thank you.
Thank you very much. So for the interest of time and to have our schedule ongoing, if you have any other questions, Professor Bradley, I think would be available online later, or you can email him. And then also, he will be staying here as a visiting professor until May. So feel free to contact him, make a proper appointment so that you would be able to talk with him, whatever concern or interest you have within this.
But even after May, you're not going to get rid of me. I'll keep coming back. But
Yeah.
I'm like a bad penny, right? I keep showing up. So, okay.
Thank you very much, Professor Bradley Nelson, for this beautiful conversation with our audience online and outside.
Thank you.
It's my turn to introduce the.
Yeah.
Hello, this one. We use this microphone because this is for professional ultra singing, and this one is for just the normal announcement. So, thank you very much, everyone. And just some questions about students wanting to join Professor Nelson's lab. Of course, as much as possible, I think there are many ways you can approach that. One thing is, of course, try to join my lab so that, when Professor Nelson will see it, then I can recommend you to join, just like Maggie. Yeah. But, there are already many students. I have 9 PhD students now, so the competition is very, very steep. But the other one is, we are not really wanting to, what the essence of inviting Professor Nelson is, of course, to enjoy the technology, but at the same time to inspire us to be like Professor Nelson. We can join him, and if we cannot join him, let's be like him. Like that, What did even Brad would say, I didn't know it will come out like this. We just work very hard, and someday things will work out, and someday you can develop something. That's the essence of this session, I think. You can look at it by joining like that, but if it's not possible, you can look at it as an inspiration that you can work towards. Yeah, thank you. And now let's go to the next activity. Normally, in my activity, I have always have an entertainment, and that entertainment will be provided by Professor Ultra. And my wife told me, if you hire someone to do the master of ceremony, to do the hosting, you have to pay him very much. Plus hosting, plus entertainment, now the payment will become double. Now Professor Ultra is doing that. He's hosting plus he's singing. So without further ado, and Professor Ultra cannot ask payment from me because I'm the one who recruited him to bring him to the BIOS. Okay, now let's do the. Okay, let's give him a big round of applause.
Thank you. So I'm really forced to do this because the actual thing is Rodrigo can't afford to hire an entertainer. He's complaining we can get money to hire an entertainer. So this is what we have to do. I'm the biggest support system for Professor Javisola here in BIOS. Okay, so protocol observes. This song is for everyone. I hope you would relate. Okay.
The radio mode aux input. The Bluetooth device is ready to pair. The Bluetooth device is connected successfully.
God bless me. Funny how a lonely day can make a person say, what good is my life? Funny how a breaking heart can make me start to say, what good is my life? Funny how I often seem to think I'll never find a dream in my life. Till I look around and see this great big world is part of me in my life. This is my life. Today, tomorrow love will come and find me. But that's the way that I was born to be. This is me. This is me. This is my life. And I don't give it down for lost emotions. I've such a lot of love I got to give. Let me live. Let me live. Sometimes when I feel afraid, I think of what a mess I made of my life. Crying over my mistakes, forgetting all the breaks I've had in my life. I was put on earth to be a part of this good world is me in my life. Guess I'll add up to the score and count the things I'm grateful for in my life. This is my life. Today, tomorrow, love will come and find me. But that's the way that I was born to be. This is me. This is me. This is my life. Don't give it down for lost emotions. I've such a lot of love I got to give. Let me live. Let me live. This is my life. This is my life. This is my life. Thank you.
Okay, please catch his breath. It's over. So the next part is the demo that's awaited by everyone. The question about if you have anything that Professor Nelson brought. Actually, we have a system here that even the catheter is there. And Lucky will do the demo, and then we will show on video. There's the robot is there in EKH Zurich, and it's ready. And yeah, it's ready now. So we have to share your screen so that we can look at it here. And after the demonstration, some of you can volunteer. Some volunteers, if the time permits, to to try the system and see if you can move the catheter around, so that maybe you will be a certified operator later when the system is already available. Yes, and we also need to have a picture before the final closing of the program.
Yeah, thank you very much, Prof. Hello, everyone. So for this demo, it's going to be an interactive demo. So I urge all our guests to come here so that I can
So
how soon will you make it? Hello. Okay. I just. Okay, so welcome to the demo session. So in this demo, we are going to demonstrate teleoperation or telesurgery, right? So what we are going to do is, so the session itself is divided into four aspects. The first aspect is the electromagnetic navigation system or the robotic system itself, which is this machine here that Professor Nelson mentioned. It is located in Zurich, and there are some people there who are making sure that we are connected with this machine here. And also on that side, they also have this guide wire. It's a magnetic guide wire. And in addition to that, they have a silicon model, which is our patient. It simulates the vessels in the brain, in the brain of the patient. So what we are going to do, we are going to guide this magnetic guide wire through the magnetic fields that are generated by this machine. So this machine is going to generate magnetic fields such that we can traverse through a very complicated structure, which is located in Zurich. This is the structure that we are going to control the magnetic guide wire on. And then the second component of the procedure, it is the control console. Control console is what you see here. Ideally, this is where the surgeon will be. You guys will get an opportunity to be the surgeon for today, and then you are going to do the operation in Switzerland. So on the control console side, we have the PS controller, which is what you're going to control the fields generated by this electromagnetic navigation system. And then also we have different views. So this is supposed to simulate the X-ray images. So this is the top view and the side view, and you also have the 3D view. So when you control with the controller here, you are going to observe the 3D view where the catheter is moving inside the vasculature, and you are going to also see the 2D images. And then, the other part, the fourth part, I already mentioned it. It is the anatomical model, which kind of simulates the vessels inside the human brain. It's also located in Zurich. The controller, then the last part is the communication infrastructure. All of this is happening over the internet. So we are sending commands here through the internet to the system in Switzerland, and the system in Switzerland also sends some commands to us here. Okay. Yes, so I'm just going to do a small simulation to show you how to operate the system. Yes, so this is the controller that you are going to use. When you press this button here, you are going to advance the catheter forward. So as you can see, when I press here, you can see the catheter is moving forward, and all of this is happening in Switzerland, right? So in this case, the surgeon will be the one advancing forward, and when you press this button, it's going to go back. You're going to retract. And then we can also generate magnetic field because we use magnetic fields to change the direction of the guide wire. So we're going to slowly advance forward. And then I will use this button here to change the direction of the fields. As you can see, the green arrows on that screen. You can see I point the arrows on that screen to the direction which way I want to go. And then when I'm in the right direction, I can press the advance button to advance forward. I can also change the direction of the fields to precisely guide the guide wire through where I want to go. So this is very, very difficult when you are using a manual guide wire because you cannot control the direction of this T. You can only push it or twist it. So, and also one of the advantages of magnetic navigation is, as you can see, we can do this procedure from remotely from anywhere in the world. But with a mechanical approach, with mechanical thrombectomy, you have to be, the doctor has to be at the same side with the patient. So now I'm going to try to point down in order to get inside of this channel here. So now, as you can see, I'm on the other branch. And when you are on the other branch, on the branch with which you want to go, you can advance forward to arrive to your location or your target location. Yes, so I will give one of you the chance to test, and then okay.
Oh, I'm so sorry. No, trying to
Okay, so this is for advancing forward, this one, and then this one is for going back. So you can just test a little bit and see what happens. You can look at this one, you can also look at this one. This is the 3D image and this is the 2D image.
So this
is for going forward. You can push and try. You can see your guide wire going up.
Yes.
You can also retract just to have a feel of what is happening.
Oh, it moves so fast.
Yeah, it moves so fast, which is really nice.
So you have to really practice.
Yeah,
or-
when you practice, yes.
So this one moves it to the side. Or
Yes, this one is when we want to turn. So you can, right now where you are, yes, you can turn this way.
do I press and turn at the same time?
No, you turn first and then you press while you are on the right direction. Yes, that is really good. Now, when you are in this branch, you want to go up, you can change the direction of the fields to point to where you want to go.
Is it going?
You have to advance a little bit forward. And then you turn the fuse, point that way, this way.
It won't pump there.
This one, this one.
Yeah.
No, it will not punch.
It will not punch
No, it will not punch the other. Because it has been made in such a way that it doesn't punch the.
So then I can retract it.
Then you
this
can
way.
retract, you can retract.
So retracting, I don't have to, I can
No.
just press,
You can just press and then you will go back.
just like that.
Yes. And then after you retract, you can choose another vessel that you want to go and try it.
Let's give somebody else a chance.
That was
Thank you.
Yes, so this is for going forward. You know, advance, yes, and that one is for going back, just to have a feel of what is happening. So, and then this one is for changing the direction. Try to change the direction. This is the scale. Now your field is pointing this way, so you want to point straight. And then you advance forward.
That's a problem.
And you have to retract the mechanism. Open the hood.
This will power.
And then a little bit more, and then you turn this one. You point the field this way. Then you can advance. Then you can advance. Now you are this way, so for you to turn, you have to also turn. Then go forward.
How long have you been?
1.5 years.
Well,
but you can also retract and have a feel of retracting and just go back to where you were.
But as we go about with your joystick, this controller, we feel the effect.
No, there is no force feedback on this one.
Yeah.
There is no force feedback. That's I would say one of the few limitations.
Yeah.
Because you cannot feel one of the advantages of manual thrombectomy is because as the doctors push the guideline, you can also feel that on the hands, but in this one you cannot feel.
Yeah, now tell me, like.
Now this one is the only one that works for the direction. This one you can just press it.
Wait,
This one is
like this
for
one.
advancing, yes. And this one is for retracting. You can try to retract.
Get it back. Oh, okay.
Now you can go forward. You go forward until yes, that one until to a point where you have to change the direction. Maybe go turn to the right there.
With which?
With this one.
What am I turning?
Yes.
The magnetic field.
Yes, you are generating the fields that are pointing in the direction of the.
So now tell me, like,
Well, I mean, these are.
how is the interference of the geographical north, on this?
It's very minimal because this is around. We operate at around 30 millitesla. Geographical, the Earth's magnetic field is very, very weak. So weak.
Very weak.
So this is there's no interference at all.
Oh. How is it so weak when we can feel it in our?
In your watches.
Yeah.
In your watch, because
You can also take it.
Delegate.
yes, but you haven't.
That aren't just.
Yeah.
It's still fun.
Then I will say home.
Currently.
Then you get scared. Well, no, this is an easier way of doing it. It takes a few minutes. Then you are right to do
So what are otherwise current this is the wire I use it.
Yes, this is the wire. This is a similar wire that they are using. Yes. Very soft.
So motho wa ba idibaditse.
Wa ba idibaditse during the process. Ano ke le ba le ba tamgani TV ke bon for Hannah this one is for retracting this one, right? You can see we are retracting, the other wire is going back. This one is for advancing. If you want to choose the direction, we use this analog key here, right? Like here,
Okay, thank you. So students, please join us here. I guess please stay. We have to take picture with our students. Okay, please come in. All other participants outside, join us here. Please, guys, for a quick one. Come. Okay. Closer. At the back, those who are taller, you can stay at the back. Panorama can work. Okay. Last one. Okay, thank you very much. Okay, ladies and gentlemen,
I would like to request Professor Chiparoro to give the closing remarks.
Let us be seated. Can we be seated, please, for the closing ceremony? Can I request that we be seated for the closing ceremonies, please? Closing remarks. Thank you very much. Thank you very much, colleagues, for cooperating. Thank you. Thank you, Master of Ceremonies, for according me the opportunity to close this or to deliver the closing remarks after a very inspiring presentation by Professor Nelson. But as a matter of procedure, I have to observe protocol. And where I come from, it doesn't matter whether the dignitary is absent or present because they are always present. So I will start, have a scripted remarks to make. They are scripted, so I will go with the script that I prepared. Professor Utuhesi Totolo, Vice Chancellor of the Botswana International University of Science and Technology, I have to recognize him in absentia. Professor Elisha Shimang, Deputy Vice Chancellor, Botswana International University of Science and Technology, in absentia. Professor Abraham Ataugo, who was here present doing the opening remarks. Deputy Vice Chancellor, Research, Development and Innovation, Botswana International University of Science and Technology. I have again to, in absentia, to recognize, because he was supposed to be a Botswana ambassador designate to Japan, Professor Buha Manasha. I don't know whether that is Buga or Buha Manasha. In absentia and in her presence, I would recognize here the Honorary Council of the Philippines to Botswana and the first gentleman with her, Ms. Anelene Vista. Let me again recognize the presence of the Honorary Council Switzerland to Botswana, Mr. Ziki Ganunu, and Ms. Julia Galfand, a Fulbright scholar and coordinator. I think she was here, she has left. She's not here. And then our main guest, Professor Bradley Nelson, Professor of Robotics and Intelligent Systems ATH, which I think is translated in English as the Federal Institute of Technology Research. Colleagues and gentlemen, I hope I would be speaking for all of us if I said this morning we have had or were treated to a world-class presentation, a presentation well delivered. It was well delivered orally, in my opinion, and it was well delivered visually. A presentation well nuanced in demonstrating and bring to the understanding of all of us, even the common person in the street, the deep and complex scientific processes that these nano robots can be put through and be used. I think we should thank the team for their stellar effort. Let me on record, and this is one of the things that I think I will be speaking for the rest of the team, that this was a testimony and a living testimony of the innovation in medical care. It involves, in my own opinion, as a non-expert, look at the configuration that was a display. I have just seen a combination of many things: telecommunication at play, nano robotics at display, or mechatronics and robotics, high resolution 3D imagery and camera, and many other enabling technologies. I think that the infrastructure that we just saw coming together in the way that it came together to deliver the treatment was just something out of this world. 3, the tremendous benefit of allowing expert surgeons to operate on a patient who may be thousands of miles away. It overcomes the geographical boundaries or barriers. This is especially critical in areas as we have been appraised. Very critical in remote rural, where medically infrastructure, state-of-the-art infrastructure medically is unavailable, where specialist surgeons, wherever they are located, they are able to work on patients. This is very good. The last one that I would want to mention here, and I think this comes at a very opportune moment, because we in the School of Electrical and Mechanical Engineering, we have just recently registered a new program, a Bachelor of Engineering program with honors in biomedical engineering. We expect to start enrolling, subject to, of course, endorsement by the medical authorities, our first cohort in the 2027-2028 academic year. So we are therefore pleased that this presentation, as it came at the most opportune time, that when we start enrolling and we are up and running with this program, we will be able to refer to the experts in the field who are leading that space. And here we should, again, I think we should thank Professor Rodrigo Jamsona, acknowledge him and thank him the best way we can for discovering Professor Nelson. I don't know who discovered the other one, but I heard him saying that they met 15 years ago in South Korea, if I heard you well. But whoever discovered the other, I think this is very good that you managed to discover each other and will be able to leverage in your expertise in this space. It is with these few remarks that I wish to thank the university executive. They were supposed to be here, they are not here because of other obligations. But they are here in spirit, of course, and we have to thank them for authorizing, firstly for authorizing this event to proceed. And for those who managed to attend, for taking time out of their busy schedule to grace it, especially Professor Abraham Atarugu, who was here with us. Professor Ultra for the entertainment. You are a good singer. We have seen you before in some of our evening cultural events performing there. We should thank Professor Nelson and his team for accepting to favor us with a free lecture. They don't come cheap, people of his caliber. I was once a consultant somewhere, and I was charging at my level back then in the day. I used to charge 2.5 an hour, but with him in modern times, he won't come that cheap. So thank you very much for giving us that, taking time out of your busy timetable to be with us and give us that lecture. The audience who too found this occasion worthy of your time. You found it worthy of your time, so, and you have put away other obligations so that you can be with us. Thank you very much. And I thank all of you, and please have a nice day and take care of yourself. Thank you very much, Director of Ceremonies. Thank you.
Thank you, Professor Teparoro, for the closing remarks. This concludes our activity this morning. Once again, it's afternoon, good afternoon, and this is your Master of Ceremony, Benicio Ultra at your service. Thank you very much.